In this lesson, we're going to talk about the sum and difference identities. So the next identities we will learn are called the sum and difference identities. These identities are used to create other, more complex identities and expand the number of angles for which we can evaluate our trig functions exactly. So the sum and difference identities look like this. We have the sine of a sum of angles. So we have angle A plus angle B. So for instance, if angle A was 15 degrees and angle B was 30 degrees, then 15 plus 30, we would be calculating the sine of 45 degrees. So the sine of A plus B is equal to sine A cosine B plus cosine A sine B. The difference identity for sine is similar, except the sine for the angle is different. So sine of A minus B is sine A cos B minus cosine A sine B. The sum identity for cosine looks very similar, but if you'll notice, when we're adding A plus B, we end up subtracting the second term in the equation. So it's cosine A plus B equals cosine A cosine B minus sine A sine B. And also, instead of the trig functions being mixed together, these are the cosines are grouped and the sines are grouped. And then the cosine is for a difference is similar, but the sign's opposite again. And lastly, for tangent, we have this. Tangent of A plus B is tangent A plus tangent B, all divided by 1 minus tangent A times tangent B. And tangent A minus B is similar, but the signs are just changed. So these, when you're learning these, I think it's best to learn them in groups. And if you learn them in groups, it's instead of looking at them as 6 separate formulas, you can look at them as, you know, potentially 3 different formulas and just remember how the signs work, you know, or something to that nature. But we're going to take a little bit of time to prove each of these identities. I know they probably look a little bit strange. I want to show you where these things come from. And then we'll explore some different kinds of problems where they can be used. So we're going to work with the sum identities for sine and cosine to begin with. And I have a diagram here which will help us understand where this comes from, at least in the best way that I've found possible. I've seen many different proofs of the sum and different identities, but I think this one kind of makes the most sense in terms of right triangle trigonometry. So I've got some angle measures here, A and B. So this is angle A and this is angle B. They make up some right triangles, and using those right triangles we can, you know, work with some definitions of trig functions and learn a little bit about those triangles, the way they're stacked on top of each other. So everything here begins with defining this length right here to be 1. And if that length right there is 1, then I'm going to highlight that I'm working on this triangle right here. So just this triangle right now. If that length is 1, let me come off to the side. So this is angle measure B, this length is 1. Then we can define how long those other sides are by working with our trig functions. So for instance, we could say, you know, the cosine of angle B, we know that the cosine by SOHCAHTOA is defined as the adjacent side over the hypotenuse. So the adjacent side I'll call x. So this would be x over 1, which means that x is just equal to the cosine of b. So this distance right here can just be replaced with the cosine of angle b. Similarly, if I call this y, then the sine of angle b, which is the opposite over the hypotenuse, would be y over 1, which means that y is just equal to whatever the sine of b is. So that right there gives us a little bit more information about the lengths of the sides of this triangle. And it shouldn't be much of a surprise that the lengths of the sides of this triangle are sine of the angle and cosine of the angle, because if you think about, a triangle in standard position along the unit circle, we've already decided that if this length is 1, this point right here has the coordinates cosine of whatever this angle is and sine of whatever that angle is. So essentially that's exactly what we've shown. Alright, so for this triangle here, and I'm going to erase the blue because I'm going to work with a different triangle in just a second, I know that the length of the bottom of it is cosine b, and this opposite side over here is sine b. Okay, now I can work with this next triangle, which I will color in red. So it's this big triangle right down here at the bottom. Now with that red triangle, and I'm going to need this space, so I'll erase all the stuff that I've written here. We can say a couple of things. So first off, we know that triangle is a right triangle. This is angle A, and this length is cosine of B. So we can just try and find out what x and y are based off of that, in the same way that we just did the other triangle. So we can say, for instance, sine A is the opposite side over the hypotenuse. So that means y is equal to sine A cosine B. And we could say that the cosine of B is x over, the cosine of A. Sorry, we're working with angle measure A. So the cosine of angle A, I'll get it right. Cosine of angle A is x over cosine B, because it's the adjacent side over the hypotenuse. So this means that length x is going to be cosine A times cosine B. So for this red triangle, the length of the bottom is cosine A cosine B. The length here is sine A cosine B. Alright, I'm not quite done yet. I still have a little bit more setup to do. I still need to work with one more triangle, and I'm going to put it in green. So this triangle right up here. Yeah, hopefully you can see that green. Alright, so that triangle in green, let me shade it a little bit more so you can see it, is we know one side. We know the hypotenuse is sine B, but we don't know any angle measures. But we can work with that. So for instance, right here, I can determine what this angle measure is. All the angles in the triangle add up to 180 degrees. We already have a 90-degree angle, so A and this angle add up to 90. So that means this angle measure is 90 minus whatever A is. Alright, now that angle, 90 minus A, plus this angle, which is 90, gives me a total of 90 minus A plus 90 is 180 minus A. And what that means is, if you think about, right here, I'll draw in blue. This total angle right here would be a straight angle. So the total angle measure would be 180 degrees. So I have 180 degrees so far. So 180 degrees is equal to, I'll call this angle measure theta. Theta plus the sum of those other angle measures. So 180 minus A. All right, so subtract 180 from both sides. These cancel. So I have 0 equals theta minus A. If I add A to both sides to finish solving, I find out that that angle measure is just A. So let me get rid of all the extraneous stuff here that I don't need. So I have my green triangle that I'm concentrating on now. This angle is A. All right, let's work with that. So we'll get rid of all this stuff. I'm going to need to use some scratch work. So for that triangle, and I'm going to draw it this way instead of tilted the way it is. So I have a right triangle. This angle right here is A, and the hypotenuse is the sine of B. Okay, so I'll call this X and call this Y, and we can say the cosine of A is going to be the adjacent over the hypotenuse, which means X is cosine A sine B, and the sine of angle A is the opposite over the hypotenuse. So that means Y is equal to sine A sine B. All right, so that's what I have here and here. So X is cosine A sine B, Y is sine A sine B. Now, I have one last triangle to work with. The last triangle that I have to work with, I'll go back to blue here because I only have 3 main colors to select from. This triangle right here. So notice I'm using that dashed line that I've kind of drawn in the end. So that triangle right there. Now for that triangle, this angle measure here is the sum of A and B. So this is A plus B. The length along the base. So from this point all the way over to this point, it's cosine A cosine B. From here to here, it's sine A sine B. So the length of this bottom side of this triangle is actually cosine A cosine B minus sine A sine B. And then the length of the upper side, the other side, if you consider from here to here, it's cosine A sine B. Then from there all the way down to there, it's sine A cosine B. This would be sine A cosine B plus cosine A sine B. All right, now the length of the hypotenuse is still 1. That was just from what we defined originally. Now what I can say is the sine of A plus B so sine is the opposite side over the hypotenuse. The opposite side is sine A cosine B plus cosine A sine B, the hypotenuse is 1. So when you divide that by 1, that's your answer. The cosine of A plus B is the adjacent side over the hypotenuse. So cosine A cosine B minus sine A sine B. And you could even define the tangent here. If you just, the tangent of A plus B would be the opposite over the hypotenuse, or the opposite over the adjacent side. And so you would just divide and simplify those terms. But we'll wait for that until later. Right now, we've established the sum identities for sine and cosine. The argument here might seem a little bit strange to you, but I don't think any bit of it is beyond your abilities. This is, just using right triangle trigonometry in kind of a different setup, and using the basic rules that we've established thus far. You should have been able to follow along and at least understand what I was doing in order to arrive at these. Now, this proof is nothing that you actually need to know for the course. I'm just showing you where these things come from. In the end, you just need the formulas, so keep that in mind. All right, let's look at tangent. Let's look at how the tangent works. So tangent of A plus B. So the tangent of A plus B is the sine of that angle, A plus B, over the cosine of that angle, A plus B. Now, in order to simplify this, we just need to substitute in what we know sine of A plus B. That is sine A cosine B plus cosine A sine B, and divide that by cosine A cosine B minus sine A sine B. And in order to get this to work out, this is one of the times where we have to multiply in something that doesn't exist already. So what we need to do is we need to multiply the numerator and denominator by 1 over cosine A cosine B. And when you do that in the numerator and denominator, these are two fractions that are equal, so this is essentially just multiplying by 1. But it's going to give us an advantage here. So the advantage you'll see as we go through. So I'm going to have sine A cosine B over cosine A cosine B plus cosine A sine B, and you have to be really careful about copying the right trig functions and equations, variables and everything. That's the numerator now. The denominator looks like cos A cos B over cosine A cosine B minus sine A sine B over cosine A cosine B. Now there's a lot of stuff that will cancel out. So let's see what happens here. So in the first fraction in the upper left-hand corner, I've got cosine B in each one of those. That's going to cancel. And then I'm left with sine A over cosine A. Sine over cosine is tangent. In the next fraction, cosine A cancels, and then I'm left with sine B over cosine B. So that is tangent B. In the next fraction, cosine A and cosine B, all of those cancel, really results in just 1. And then lastly, sine A over cosine A is tangent A, sine B over cosine B is tangent B. And there we've established the formula for tangent of a sum of angles. And then finally, the difference identities. You can do the same sort of argument. You can draw a triangle setup to make this work out, but there's a much easier way. So for instance, if you think of sine of A minus B as A plus negative B, then what you're going to evaluate is sine A cosine negative B plus cosine A sine negative B. Well, we've learned the negative angle identities, and the cosine of a negative angle we learned is the same sign as the cosine of a positive angle. So sine A cosine B is what that turns out to be. Sine of a negative angle results in changing the value of the sign. So we have a negative cosine A sine B. And the argument is the same for any of the remaining ones. So cosine A plus negative B is going to be cosine A cosine negative B plus sine A sine of negative B. Cosine of a negative angle is positive, so cosine A cosine B. Sine of a negative angle, whoops, I'm sorry, for cosine when you add, this is a minus. Sine of a negative angle results in a negative, so it changes the sign in between, which becomes positive. Sine A, sine B. And lastly, for tangent, it works the exact same way. So I'll just do it quickly. Did the same thing again. This was supposed to be plus here and 1 minus tangent because I'm using a sum identity here. I just copied my difference identity. But this turns into the difference identity. That's the point. Okay, so you know where all of those come from. Now let's take a look at how they could be used. So let's evaluate sine of 75 degrees. Now, if you get out your unit circle, 75 degrees is not an angle measure that we generally know how to do. We know 30 degrees, 45 degrees, 60 degrees, 90 degrees. We don't know 75. So let's see what we could do to work that out. So if you notice, sine of 75 degrees could be decomposed. We could write it as the sine of, say, 30 degrees plus 45 degrees, or 60 plus 15, although we don't know what the exact value for the sine of 15 degrees is. But 30 and 45 we both know. And this is the sum of two angle measures, so we could write this now as the sine of 30 degrees times the cosine of 45 degrees plus the cosine of 30 degrees times the sine of 45 degrees. So using my sum identity, this is what I come up with. Now, all of these values are known. So for instance, you could get your unit circle out if you like, but the angle measures from 0 to 90 degrees, you should get to the point where you know those kind of on top of your head. So the sine of 30 degrees is 1/2. The cosine of 45 degrees is the square root of 2 over 2. The cosine of 30 degrees is square root of 3 over 2. And the sine of 45 degrees is square root of 2 over 2. If we simplify this, we would have square root of 2 over 4 plus the square root of 6 over 4, or square root of 2 plus the square root of 6 divided by 4. And that's the exact answer for the sine of 75 degrees. So this can be used to expand the number of places that we can evaluate our trig functions. Evaluate tangent of 11 pi over 12. So we can do the same thing here, although it's probably going to be easier in terms of degrees rather than radians. It's just going to be easier to decompose this into angle measures that we know we can work with. So I'm going to take a second to just change 11 pi over 12 into degrees. So 11 pi over 12, remember we multiply, it's either going to be by 180 over pi or pi over 180. If you're unsure, just remember you've got to get that pi to cancel out. So 180 degrees over pi, so you can get that to cancel. So 12 and 180 are both divisible by 12. But if you didn't realize that, if you didn't know that, you could in fact work with, say, like 6. You could definitely see that 180 and 12 both go into 6, and then just continue dividing out the remaining factor of 2. But if I take 180 divided by 12, that gives me 15. And then 11 times 15 is 165. So this is 165. I don't know why that degree is so large. 165 degrees. Which that is going to be easier to decompose. And we could say, so we're looking for tangent of 165 degrees. I could do this as tangent 120 degrees plus 45 degrees. That would work just fine. I just need to be careful of, sines, depending on what quadrant I'm in, that sort of thing. All right, but this is going to be it's the tangent of the first angle, so tangent 120, plus the tangent of the second angle, divided by 1 minus tangent 120 degrees times tangent 45 degrees. All right, so tangent 45, that's an easy one because sine and cosine are equal at 45 degree angle measure. That's 1. But tangent 120, if you want to grab your unit circle, that's simple enough to do. So here's 120 degrees. This is my sine, and this is my cosine. So tangent is going to be root 3 over 2 divided by negative 1/2. If you invert and multiply, the 2's are going to cancel out and leave you with negative square root of 3. So there's tangent of 120. So I'll plug that in. So this is negative root 3 plus 1 over 1 minus negative root 3 times 1, which is 1 minus the square root of 3. This would change into a plus, so 1 plus the square root of 3. Now, that can be simplified a little bit further. If you have a square root in the denominator, you're supposed to get rid of that. And you can get rid of that square root by multiplying, in this case, by the conjugate, 1 minus root 3 over itself. And when you do that, you set up the difference of squares down in the denominator. So like in the numerator, it's going to be, you have to FOIL these things. So 1 times 1 is 1. 1 times the negative root 3 is negative root 3. Negative root 3 times 1 is negative root 3. Negative root 3 times negative root 3 is positive 3. In the denominator, you have the difference of squares. So it's similar. 1 times 1 is 1. 1 times negative root 3 is negative root 3. Positive root 3 times 1 is positive root 3. Positive root 3 times negative root 3 is negative 3. So this middle term cancels out of the denominator and gives me 1 and 3 can combine to 4, and the minus 2 root 3, and in the denominator 1 minus 3 is negative 2. So when I divide, I can divide both of these by the negative 2. So negative 2 plus root 3, or 3 minus 2, or square root of 3 minus 2, either way should be fine. And that is the fully simplified answer. Next up, find cosine of x plus y if cosine of x equals negative 8 over 17 and cosine of y equals negative 3/5 with x and y in quadrant 3. Okay, so in order to work this through, one thing that we know here is cosine of x plus y, which is what we're trying to find, is cosine x cosine y minus sine x times sine y. We already know what cosine x and cosine y are. Those are given to us, but we don't know what sine x and sine y are. So let's try and figure those out. I'm going to come off to the side and just do a little bit of right triangle trigonometry. So I'll say this is angle measure x. And I know that the cosine of x is negative 8 over 17. So the cosine of x is negative 8 over 17. We know cosine is the adjacent side over the hypotenuse. So this would be like negative 8 and 17. So we can find this distance, which I'll call a, by using the Pythagorean theorem. So negative 8 squared plus a squared is equal to 17 squared. So this would be 64 plus a squared, and 17 squared is, let me grab my calculator, whoops, 289. And when I subtract 64 from both sides, I get a squared equals 225, which its square root is 15. And it would be positive or negative 15 depending upon the quadrant that we're in. So we're told that we're in quadrant 3. So the only thing that we need to really worry about here is that the sign of our angle measure, so the actual trig function sign, is going to be a negative. All right, so here's what I know so far. Cosine xy is cosine x, which is negative 8 over 17. Cosine y was given as negative 3/5. Then it's minus sine x. All right, so the sine of x, and x is in quadrant 3. This needs to be a negative number. So I'm just going to say that this value a is 15, like we solved. That's the opposite side of my angle. opposite over the hypotenuse is the sine. And I'm just going to write that thing is a negative, because I know in quadrant 3 it's supposed to be negative. So you just choose the sign based off the quadrant that you're in. All right, now y, and if you wanted to make this a little bit more clear, so like in quadrant 3, so I'm going to draw like this, so this would be quadrant 3. And I can put my reference triangle in quadrant 3. All right, so I'll call this y right here. All right, so the cosine of y is -3/5, which is the adjacent over the hypotenuse. So we just need to figure out what this distance is right here. So -3 squared plus b squared is equal to 5 squared. So 9 plus b squared is equal to 25. So b squared is 16. Or b is positive or -4, but since I'm in quadrant 3, it's going to be -4. So the sine of this angle measure is going to be -4/5. And now I just need to simplify everything. And I can't promise that it's going to be pretty from here forward, but it won't be difficult to do. 8 and 3 will multiply to 24. 17 and 5 multiply to 85. -15 times -4 is going to be positive, so this is still going to be minus. 4 times 15 is 60. And 17 times 5 is 85. And 24 minus 60 is -36 over 85. So that is the value of the cosine of x plus y. There's potential that you might be asked to prove an identity using a sum or difference identity. So for instance, cosine of x minus y divided by sine x sine y is equal to cotangent x cotangent y plus 1. So let's see what happens here. In these identity problems, you just kind of start with identities that you know, plug them in, see where they lead you, and go from there. So we do know an identity for cosine of x minus y. That is cosine x cosine y plus sine x sine y, and that would still be divided by sine x sine y, which we can split up into two different fractions. So cosine x cosine y over sine x sine y plus sine x sine y over sine x sine y. And the first fraction, cosine over sine, is cotangent. So cosine x over sine x is cotangent x, and then I have cotangent y, force of habit. And sine x over sine x cancels, same for sine y over itself, so this just becomes plus 1. And then we've proven that identity. Here's another type of problem you might run into. Find the exact value of the expression sine of 5 pi over 12 cosine pi over 4 plus cosine 5 pi over 12 sine pi over 4. So similar to the one we did before, but if you look for 5 pi over 12 on your unit circle, that's not one of the standard angle measures that we work with. So you're not going to be able to solve this using the unit circle as is. One thing that we might be able to do, however, is use the sum and different angles or identities in reverse. So for instance, 5 pi over 12 plus pi over 4 would be 5 pi over 12 plus 3 pi over 12, which is 8 pi over 12, or if you divide the numerator and denominator by 4, that's going to be 2 pi over 3. Now 2 pi over 3, if you look at your unit circle, is one that's known. So we're going to work with that. Now, the form of this, sine of an angle times the cosine of a different angle plus cosine of the first times sine of the second, that is the form of our sine of a sum of angles. So we can say here that this thing right here is equal to the sine of the sum of 5 pi over 12 plus pi over 4. And we just showed that these add up to 2 pi over 3. So essentially all we want to know then is what is the sine of 2 pi over 3, and that's going to be the y value of our unit circle. So root 3 over 2. All right, lastly, another proof of an identity. So we've seen this identity in the past. Cosine of 90 degrees minus theta is equal to sine of theta. But we can actually prove this in a little bit more rigorous manner than what we did in the past by using the sum and difference identities. So we know cosine of x minus y is cosine x cosine y plus sine x sine y. And using that, we could say cosine of 90 degrees minus theta would be cosine of 90 degrees times cosine of theta plus sine of 90 degrees times sine of theta. And cosine of 90, sine of 90, if you think of your unit circle, 90 degrees is here. So this point on the unit circle would have the coordinates 0, 1. So the cosine is 0, and the sine is 1. So this goes to 0. 1 times anything is just itself. So there's a little bit more rigorous way of proving that that is the case.